Hello everyone, welcome to the 8th video of our lecture series. So in this video we are going to solve some problems from different textbooks. So now we are not solving questions from previous year, but these questions also important to brush up your concepts. So let us do our first problem. Okay, so the problem states that we have an electron that is moving freely inside a one-dimensional infinite potential box with walls at x at 0 and x at a. So we have an one-dimensional infinite potential box. So this is infinite and this is x0, this is xa, and the particle is moving here in this region, and we have potential to be 0. This height is potential height is infinite. So we have an this infinite potential box, we have an electron here. So if the electron is initially in the ground state of the box, so what will be the state of the electron? So its wave function is phi 1x, it is root over 2 by a sine pi x by a. So this is the ground state wave function of the electron, and this state has energy value pi square h cut square by 2 m square. That is standard result, and that we all know. Now if we suddenly quadruple the size of the box, so what is the meaning of this term? That means we are changing the size of the box suddenly. So now the box has this shape. So this is x0, but this is x equal to 4a, and this is infinite potential. So now the electron is able to move in this region from x equal to 0 to x equal to 4a. So we have to calculate the probability of finding the electron in the ground state of the new box and the first excited state of the new box. So let us do our first question. So we have to find the probability of finding the electron in ground state of the new box. So the new box has length now 4a. So if we denote this by a, so what will be its ground state wave function? So ground state wave function will be root over 2 by a sine pi x by a. So let us put the value of a. So it will be 1 by 2a sine pi x by 4a. So that is our ground state wave function, and it will have energy. So let us write the energy. It will have E1 dashed pi square h cut square by 2m, and a has value 4a, so it will be 16a square. That means pi square h cut square by 32 m square. So we have to find the probability of finding the electron in this state. So what is the probability? So the probability of finding the electron in the ground state of the new box is so what is the probability? It is psi mod square. So we can write this as 0 to a psi 1 star psi 1 phi 1 dx. So let us look at this limit. So why this limit is a? Because we know that phi 1, that is only have non-zero value for x equal to 0 to a, and outside that region phi 1 is 0. So basically phi 1 is not 0 for x equal to 0 to a and 0 otherwise. So that is why this limit is from 0 to a. So let us do the evaluate the integral. So it is 2 by a, and we will have 1 by 2a, and in the integration we will have sine square pi x by 4a. So not sine square now, sine pi x by 4a and sine pi x by a dx 0 to a squared. So we have to evaluate this integral. So what will be the value of this? Let us do that. Sine pi x by 4a sine pi x by a dx. So we know that, let us do it. So we know this formula, that 2 sin a sin b is cos a minus b minus of cos a plus b. So we can write this as 0 to a, so it will be cos 3 pi x by 4a minus cos 5 pi x by 4a, and let us do that. So it will give us half, and from the first term, like, we will get 3 pi by 4a, and doing the integration of cosine will give us sine 3 pi x by 4a, and we have to put the limit from 0 to a, and in the second term we will have half by 5 pi into 4a, and this integration will give us sine 5 pi x by 4a, and this limit is also from 0 to a. So what will be the value? So let us take 4a by pi as a common factor. So from the first term we have 1/6 into sine 3 pi by 4 minus 110 sine 5 pi by 4. So let us put the value of this. So this is pi by 4, and this value is like plus pi by 4. Yeah. So pi by 4, we know that 1 by root 2. So 4a by pi, and we have here 1 by root 2, and we have 30. So it will be 5 and it will be 3. So that is the value of this integration. So let us simplify this. So 5 plus 8, 32a by 20 pi. So that value we are getting from doing this integration. So let us write down the value of p. So it will be 1 by a squared, and we have 32a by 30 root 2 pi this squared. So what we are getting? So we are getting 32 into 32, and we have 32 pi squared. So if we simplify this, what we will get? 15. It will be 15, 16. So we will get 128 by 15 squared pi squared. So that is the probability. So of finding the electron in the ground state of the new box. So in that similar manner, we can calculate the fast excited state, like the probability of finding the electron in the fast excited state of the new box. So let us do that. So fast excited state, we write this as psi 2, and we can write this as root over 2 by 4a sine 2 pi x by 4a. So it will be like 1 by 2a sine pi x by 2a, and we have our psi 1 to be root under 2 by a sine pi x by a. So we have to find the term this. So this will be our probability of finding the electron in the first excited state of the new box. So let us do that integration again what we have done for the previous one. So it will be 0 to a psi 2 star x phi 1 x dx, and we have it squared. So phi 2 and psi 2, this will give us like 1 by 2a multiplied with 2 by a, and in the integration we have 0 to a sine pi x by 2a multiplied with sine pi x by a, this squared, and we have to take its small value. So let us do this. This is again straightforward like the formula that we have used before. So using this we can write that as half 0 to a cos pi x by 2a minus cos 3 pi x by 2a. And for the first one we will get pi by 2a sine pi x by 2a, and limit is from 0 to a, minus we have here 3 pi by 2a, and we have sine pi x 3 pi x by 2a, and this limit is also from 0 to a. So for the first term we will get a by pi, and here if we put x equal to a, so it will be sine pi by 2, that means 1. And for the second term a by 3 pi, and this is like sine 3 pi by 2, so it will give us 1 again. So what we are getting, so 2a by 3 pi. So let me check this once. So we are getting sine 3 pi by 2, so yeah, it should be minus 1, so it is minus 1. So if we put here plus, so we will get like 4 pi. Yeah, just check this calculation once. It is we have to do this calculation just and nothing else. So p2 value we will get as 1 by a squared into square root of this term, so it will be 16a squared, and in the denominator we have 9 pi squared. So we are getting 16 by 9 pi squared. So that is our probability of finding the electron in the first excited state of the new box. Let us move to the second problem. So what does the problem states? We have a particle of mass m that is subject to an attractive delta potential which is given here, and V0 has the dimension of energy plus into distance, because we know that delta function has dimension of in inverse length in 1D. So first we have to show that in case of negative energies the particle has only one bound state, and we have to find the binding energy and the wave function for that state. After that we have to calculate the probability of finding the particle in the interval from minus a to a, and then we have to calculate the probability that the particle remains bound when V0 is halved suddenly and quadrupled suddenly, and we have to also study the scattering case, that means E greater than 0, and calculate the reflection and transmission coefficient as a function of the wave number k. So this is all we have to do. So let us proceed. So first we have to know why there is only bound state for E less than 0. Why not for E greater than 0? So if you look at the potential, it has of the form minus V0 delta X. So for what is the condition for bound state? We know for bound states we have to have energy which is less than potential at x tends to plus minus infinity. And for this given potential, so it is basically we have our x dimension here, and if this is our potential value, then we can see for only x equal to 0 we have an negative delta potential, and for the rest we have our potential to be 0. So potential at plus minus infinity, this is 0. So that is why energy has to be less than 0 for bound state. And what is the scattering state case? For scattering state case, we have energy greater than 0. So this we have cleared that why energy should be 0 for bound state. So now let us calculate what we have to do. We have to show that this particle has only one bound state, and we have to find its energy and wave function. So as we have to find the wave function, so we have to start with Schrödinger equation. So let us start. Let us write down the Schrödinger equation in one dimension. So we have our Schrödinger equation here. So this potential, it is 0 for x not equal to 0. So let us do that case. So if x not equal to 0, then we will have Schrödinger equation to be h cut square by 2m del 2 psi del x square, which should be equal to E psi, because potential is 0. So del 2 psi del x square will give us 2m E by h cut square into psi. Now note that for bound state E is negative. So we can write E to be like this. So this is our value and this is the negative coefficient. So and this is positive. So if we put E here, so we will get 2m E by h cut square psi. So we can denote this by k square. Let us denote this by k squared. So this is our k squared. So we can write psi to be like, suppose a e to the power, suppose a e to the power ikx plus b e to the power, sorry, it will not be ikx, it will be just kx, and b e to the power minus kx. So that is our wave function for x not equal to 0. So now let us consider for x less than 0 what is the case. So for x less than 0, if we consider this term, then what we will get? So if we put here x tends to minus infinity, this term will diverge. So this is not a physically acceptable solution. Not physically acceptable for x less than 0. So for x less than 0, we have our psi x to be, so let us denote this by psi minus x, and it is, let us write this a, capital A. These are just constant whose value we have to find. So this is for x less than 0, and if we apply the similar concept, similarly we can see that for x greater than 0, this term will diverge. So we will have psi x in x greater than 0 to be of this form. So this is for x greater than 0. Now we know that psi x is continuous at x equal to 0. So wave function must be continuous because wave function square denote probability, and if wave function is not continuous, so at a given point we will have two different probabilities of finding the particle at the same instant of time, so which is not possible. So that is why wave function should be continuous. So by applying the continuity condition at x equal to 0, we can write that psi minus and psi plus at x equal to 0 should be same. So that means a and b should be should be equal. So that implies that our wave function is a e to the power kx. So you can denote this by this modular factor. So this is our physically acceptable wave function for x less than 0 and x greater than 0. And we also know that the first derivative of psi is continuous. So we know that in general it should be continuous, but is it true for delta potential? So let us find out. So we have our Schrodinger equation. Okay, so that should be minus, yeah, because for x greater than 0 we have mod x to be x for x greater than 0 and minus x for x less than 0. So let us do the integration. So suppose we are integrating this from minus epsilon to epsilon. So epsilon is tends to 0. So that means within the region 0, within the region x equal to 0 where we have this delta potential, so we are integrating this from minus epsilon to epsilon in a very small region. So what from the second time we will get v of x psi of x dx, and that is from minus epsilon to epsilon, and energy we have psi of x dx from minus epsilon to epsilon. So if we take the limit now epsilon to be 0, so let us take limit epsilon to be 0. So this term, like limit epsilon to 0 minus epsilon to epsilon psi x dx, that should give us 0, because as epsilon tends to 0 we are converging to x equal to 0 point, and as we do the integration, so it will give us 0 because psi x is continuous. So the right hand side term it will be 0. So let us consider the first term. So what we have, minus h cut square by 2m. So this will give us integration of del psi del x, and it is from minus epsilon to epsilon. So from first term we are getting this. So minus limit epsilon tends to 0 h cut square by 2m, we have del psi del x at x epsilon minus del psi del x at x minus epsilon. But in this region we know psi is psi plus, and in this region our psi is psi minus. So you can write this as minus limit epsilon tends to 0 h cut square by 2m del psi plus del x at x epsilon minus del psi minus del x at x minus epsilon. So this is we are getting from the first term, and from the second term what we are getting, we are getting limit epsilon tends to 0, and here we have minus infinity to infinity, and what is v? V is minus v0 delta x, and we have our psi x dx. Now we know that delta function integration formula, which is given like this. So this will be psi c if c is in the range between a to b, and it will give us 0 if c less than a or c greater than b. So if this c it lies within this two integration limit, this function will give us this, and if it doesn't lie within that limit, this will give us 0. So we can write this as x minus 0. So 0 is in this limit, within this integration limit. So this will give us minus v0 into psi 0. So that is we are getting from the second term. So if we write down this, now we will get minus limit epsilon tends to 0 h cot square by 2m del psi del x at x epsilon minus del psi minus del x at x minus epsilon. And from the second term, so we can write this in this side, you will get v0 psi 0. So now what is psi plus? Psi plus is a e to the power minus kx. So let us calculate this. So del psi del x will give us minus ak e to the power minus kx, and limit epsilon tends to 0 del psi plus del x at x equal to epsilon will give us minus ak. Similarly, psi minus is b, as b and a both are same, that we derived from the first continuity condition. So you can write this as e to the power kx. So del psi minus del x limit epsilon tends to 0 at x minus epsilon will give us minus so it will give us plus, so it will give us plus ak. So if we put this two value here, so we will get h cot square by 2m, and we have 2ak which is equal to v0. And what is psi 0? So psi we know that it is a e to the power minus kx. So psi at x equal to 0 will give us a. So in the right hand side we have a. So what will be the value here? K. So k is, a will be cancelled out, and it is mv0 by h cot square. So we know also that k is root over 2m root e by h cot square, and it is equal to mv0 by h cot square. So we get e to be m v0 squared by 2 h cot squared. But our energy is defined as this. So we have our energy to be m v0 square 2 h cot square. So you can clearly see that there is only one value of energy. So that is why we have only one bound state. So there is only a fixed value of energy for which we will get bound state. So now we have to find the bound state. So we have shown that this particle has only one bound state, and we have also find its energy. Now we have to find the wave function. So wave function we have already found. So just we have to normalize this. So wave function is a e to the power minus kx. So by normalizing condition, we can write from minus infinity to infinity psi star psi, this should be 1. So we can write this as minus infinity to 0, and in this limit psi is a e to the power minus kx. So a square e to the power minus 2kx, and in this limit we have a square e to the power 2kx. So from the first term we will get a squared by minus 2k, and it will give us minus 2kx. So this is from minus infinity to 0, and so I think so in the limit, yeah, it should be positive and it should be negative. So it is positive and it will also be positive, and from the second term we will get a squared by minus 2k, and we will have e to the power minus 2kx, which is from 0 to infinity. Yeah, so a squared by 2k we can take common, and if we put 0 here it will be 1, and e to the power minus infinity will be 0. And similarly from the second term we get a squared by 2k, so here is a minus, and so it will also be 1. Yeah, so because this will give us 0 and 0 minus 1, so it will be minus 1, and this minus will give us plus. Okay, so we have a squared to be k, and we found a to be root under k. So what is our wave function? Our wave function is 1 by so a have value to be root k, so our wave function is root over k e to the power minus k mod x. So then we have k 2m e by h cut squared, and e also we found out to be mv0 squared by 2 h cut squared. Let me check once. Yeah, so if we put that, so it will be 2m by h cut squared, and we have mv0 squared 2 h cut squared, so we will have mv0 by h cut squared. So that is the value of k. So psi x will be root under mv0 by h cut square e to the power minus mv0 by h cut square into mod x. So that is our the bound state wave function, and it has energy value to be minus mv0 squared by 2 h cut square. So that is it for the first problem. So in the second part we have to calculate the probability of finding the particle from minus a to a. So that we can easily find out. So probability of finding the particle between x minus a to x plus a will be minus a to a psi x square dx. So that is our probability, so that you can easily calculate. Psi x is this, so we have k, and from minus a to a we have e to the power minus 2k mod x dx. So let us evaluate this integral. So minus a to 0 e to the power 2kx dx, and 0 to a e to the power minus 2kx dx. So what will be its value? So we will have 1 by 2k, and we will have here, so this should be not here, so 1 by 2k and e to the power 2kx, it will be from 0 minus a, and here we will have k 1 by 2k e to the power minus 2kx, and that is from a 0. So first term will give us half 0 minus e to the power minus 2k, and second term will give us half e to the power minus 2k minus 1. So we will get 1 minus e to the power minus 2ka. So 1, let us put the value of k, minus e to the power minus 2m v0 a by h cut squared. So that is the probability of finding the particle between x equal to minus a to x equal to plus a. So let us now move to the third question. So what is our question? So now we have to find the probability that the particle remains bound when V0 is halved suddenly and quadrupled suddenly. So here two cases we have to consider. So just let us consider a generic potential change. Suppose we change the potential V0 to V1. That means now we have the potential V1 delta x. So for that case we have to find what is the probability for the particle to remain bound. So if V0 is changed to V1, so we will have the new wave function So if the particle is remains bound, then we will have the new wave function, that is obviously bound state, to be. So let us denote this by psi 1. So it will be root under mv1 by h cut square, and we have exponential minus mv1 by h cut square mod x. So you have to, so what will be the probability? The probability is psi 1 psi mod, and its mod value squared. So let us do this integration. So we have here like m by h cut square. Here we have v0 multiplied with v1, and we have the integration which we have to evaluate, minus m v0 plus v1 by h cut square multiplied with mod x, and we have to find so this is basically squared, so we have to find its squared value. So we will get, so this is, and from here we can write 2m by h cut square. So because this is an even function, so we can change the integration limit from 0 to infinity, and we can take a 2 out. So this is v0 v1 0 to infinity exponential minus m v0 plus v1 by h cut square into, so we have to v0 plus v1, so we can write, we have to write this as x now. So, and this is the probability, so we will get 2m by h cut square to v0 v1. So what is this integration will give us? We know that 0 to infinity e to the power minus ax dx. If we evaluate this integral, so we will get like 1 minus a e to the power minus ax, and this limit is from 0 to infinity. So by putting that, we will get, it will give us 1 by a. So this integration will give us 1 by this term. So by h cut square, so we can write h cut square in the upper portion. So, and this is squared, so we are just getting 4 v0 v1 by v0 plus v1 squared. So we have two cases. First, potential is halved, that means v1 is v0 by 2. So for that case, what will be the probability? Let us denote this by p1, and it will be 4 v0, this is v0 by 2, and we have 3 v0 by 2 squared. So we are getting p to be, so we have v0 cancelled out, and we are getting 4 product with 4, and in the lower portion we have 2 product with 9, so this 8 by 9. So that is the probability, and let us find the value for when the potential is quadrupled. That means V1 is V0. So for that case we have our probability to be 4V0, and V1 is again 4V0, and in here we have 5V0 squared, that means 25V0 squared. So we will get 16 by 25. So that is the probability of finding when we halve the potential, and that will be the probability of finding the particle in bound state when we quadruple the potential. So now let us move to the last part of our problem. So what does this state? It state that study the scattering state, that means E greater than 0, and calculate the reflection and transmission coefficient as a function of the wave number k. So let us proceed with that. So we know that here E0, this corresponds to the free motion of the particle, and for free motion, so if we write down the Schrodinger equation here, h cut square by 2m del 2 psi del x square plus v psi equal to e psi. So here v is 0 and e is positive, so psi will give like suppose a e to the power ikx plus, let us write this first as small, and b e to the power minus ikx. So this will be the solution both for x less than 0 and x greater than 0. Now are all the coefficients non-zero? So let us check. So suppose that the particle is coming from the left. So what does this term signifies? And this term signifies for the particle coming from left, that means for x less than 0 case. So in that region, so suppose this is 0, so in this region this term represents a plane wave that is incident from the left. And what does this term signify? This term signifies a plane wave so this term signifies plane wave that is reflected from x equal to 0. I mean that is reflecting back in this region. So this is represented by this and this is represented by this. But for x greater than 0, as the wave is coming from this direction, so no wave is coming from this direction, so there should not be any reflection in this side. So we can write our wave function to be a e to the power ikx plus b e to the power minus ikx for x less than 0, but for x greater than 0 there should be no reflection. Because no wave is coming from this direction, where we have considered that we have one plane wave that is coming from left. So for x greater than 0 we will get c e to the power ikx. So that is for x greater than 0. So if we again use continuity equation, then we will get psi plus at x equal to 0, psi minus at x equal to 0, both should be same. So we will get a plus b equal to c, and from the first derivative we have our condition, we have derived that condition previously. So that is our this condition. So let me check. Yeah, so that is our condition, and if we put this value, this wave function values, and do this mathematics, we will get the second continuity equation to be ik c minus a plus b plus 2mv0 by h cut squared multiplied with c. This should be 0. So if we solve these two equations now, then we will get like we have b. If you can solve this easily, so we will get b by a, which will turn out to be 1 by 1 plus I k h cut square by m v0 and c by a, which will turn out to be 1 by 1 minus I m v0 by h cut square k. So reflection coefficient will be so what is deflection coefficient? We know that b is our wave function of the reflected state and and a corresponding to the wave function of the incident. So deflection coefficient will be defined as b by a squared, and it turns out to be 1 by 1 plus h to the power 4 k squared by m square v0 squared. And similarly transmission coefficient t it will be c by a squared, because c corresponds to the wave function that transmitted in x greater than 0, and a corresponds to the wave function that is incident from the left. So t will be 1 by 1 plus m square v0 squared by h to the power 4 k squared. So this is the reflection and transmitted coefficient in terms of the wave number. Now we can express this in terms of our energy. So R will be 1 by 1 plus 2 h cut square E by m v0 squared, and transmission coefficient is 1 by 1 plus m v0 squared by 2 e h cut squared. And we know that, so this is for side check, we know that the summation of reflection coefficient and transmission coefficient should be 1. So let us just check that. So r plus t, we will get m v0 squared by m v0 squared plus 2 h cut square e, and transmission coefficient is 2 e h cut squared by m v0 squared plus 2 e h cut squared. So if you do the summation, then we can see that r plus t is 1. So our reflection coefficient and transmission coefficients are perfectly fine. So these are our reflection and transmission coefficient in terms of our wave number k, which we are asked to find in the given question. Okay, so that is it for this lecture. So we will meet on our next lecture video.